So I'm going to present the local EGA, a portable toolkit to secure, deposit, and share human-sensitive data. My name is Fred, and I work at CRG in Barcelona. And the local EGA is connected to the EGA. So this is the EGA mode of operation, and I want you to focus your attention first on the left. So you have different type of roles. At the bottom, you have the anonymous user that can browse the catalog, the different files that are available at the EGA, so through a web page. Then you have the requester type that can download those files, and of course they need to request access for it. The access is granted by a data access committee. And then finally there is the submitter, so the one that wants to upload some of the files, and the files are sequence type, phenotype, and arrays, and they need to be encrypted and then uploaded to some sort of Dropbox. And the submitter also manipulates another type of data, which is the metadata, so the information about the files themselves, and upload them in multiple ways. So in the end, what you end up with is at the bottom, you have some websites to browse the different files. You have in the middle an encrypted archive, and then a zone where people can drop their files. So this was the EGA in a second. And the presentation here is how to extend the EGA so that you also have local EGA inboxes and local EGA archives in different countries. Now, I'm going to present the overview and the general idea behind it, and a particular implementation, three particular implementations will be presented in the next presentation by Lucille. So on one hand, you have the EGA, and we know that it is run by two countries, UK and Spain. And historically, the EGA started with the three Nordic countries, Scandinavian countries, and there are also interests from France, Portugal, Switzerland, Greece, Germany, Luxembourg, and also Spain, so other part of Spain, that wanted to join and showed interest in the project. So in this presentation, I'm going to pick Sweden because it's just close to my heart and I can choose. On the left side, you have central EGA, and on the right side, you have local EGA. So as you know, that you have the submitter. The submitter manipulates two types of data, the encrypted files and the metadata. And the idea is that we want the metadata to go to central EGA, and the encrypted files should stay in the country itself where they were uploaded. And the idea is that the metadata can go across the countries, and the encrypted file should stay in the country. So the submitter makes the submission in two parts. So the encrypted file go into some sort of inbox, and when there is a trigger sent from central EGA to the local EGA, the game is to actually move the encrypted file from the inbox into a vault, an archive, and I will show you why we do not need a re-encryption. So there is the other type of user, which is the requester. Now, the requester will make a quick call to central EGA to ask if they have permission, and when they have permission, they will download the file from the country where the file was uploaded. And you probably know that why we do all that, but this is because of GDPR. Files, encrypted files are sensitive. Well, they are encrypted, so they are not that sensitive, but the original file is sensitive information, and it cannot go across borders, but the metadata is not sensitive information, and it can go across borders. So in this presentation, I will divide the presentation in two parts. So the first part is the ingestion part. The second part is the distribution part, and I start with the ingestion part. So assume that you have an account at the EGA, so you have a user login and password. What we do is we connect the central EGA to the local EGA with a very strong connection, fault tolerant, network fault tolerant. So this is a technical thing, but imagine that there is a very good connection between the two. And the first thing that the user will do is upload the files to the inbox. In order to do that, the inbox needs to know who this user is and if they have the right password. So for that, we need to find the user list and the credentials. And central EGA centralizes the user list and credentials. Then the second part is that this inbox should, of course, have some sort of security so that one user cannot see the files of another user. And then when a file is uploaded, a notification is sent to the central EGA so that we know and can display it on the web page that there is a new file uploaded. in case they want to include that file into their submission. And so the second step would be to go and do a submission, so that you construct the metadata related to those files, but the files are in another country. So after that, there is a trigger from Central EGA that says, find the file in the inbox, move it to the vault, and then tell us when you are done. And finally, we attribute a unique identifier across the whole EGA ecosystem to that file. So we call that a stable ID or an accession ID. And we attribute this file, we communicate it back to the local EGA. So this was basically the step for the submitter. And as you know that there is one part which is related to the upload at the local EGA of the encrypted file, and then there is metadata submission. Just a quick word about the metadata submission, but we have built a submitter portal where we help the user to build the submission in a web-based manner. And we want the user to not be stopped at every step of the submission because it might be a complicated step. So we have different statuses for the submission and we allow them to progress. So it's not from 0 to all, it could be intermediate steps. So what will happen is that you create a new submission. So on the top right, you will see new submission. When you create a new submission, you can enter a title, a description, and then the user will fill in the different sections related to the metadata. And the metadata will be, in the end, the user will describe the different runs, the different experiments, the different studies, samples, analysis, data sets, but also very importantly, they will describe what are the policies for those data sets and who are the data access committee, because Central EGA does not own the file, the data access committee do. So this is for web-based submissions, but of course there is also another way to submit your metadata, which is with the REST API. And this is programmatic and is very well suited for big submissions, because if you have 2,000 samples or something like this, then you don't want to go to a web page and click the next button and the next button and so on. So web-based submissions are suited for small submissions and programmatic way for big submissions. So this was the EGA. Now, when you want to introduce a new country, and I pick this one, go figure why. So what we need to do is very simple. We just make a new connection between Central EGA. So basically we clone the previous connection and we change the password. So you end up with 2 connections, and it's a very easy, secure connection between the two. So there are multiple advantages. So we have chosen a technology that is quite strong. The user credentials is centralized so that you don't end up with a situation where you have a user and a password in each country, and when the user updates their password, you need to communicate that either to all the countries or you will have discrepancies. So it's much simpler to have it centralized. You have the security and isolation, and it's easy to introduce a new local EGA. But there is one major advantage, is that we are using Crypto.jet. So let me describe Crypto.jet in a second for you. Imagine you have the original file, you encrypt it using an algorithm, you end up with encrypted data, and you used a key to encrypt the data, and you use the same key to encrypt and decrypt the data. So often you can call that a symmetric algorithm. And what we do is we package this key inside the file at the beginning of the file, and we encrypt the key, the header itself, we encrypt it so that the only those that have the key to decrypt the header could actually decrypt the blue part. The advantage is that we will split the header from the encrypted data. So the encrypted data will go into the vault, the header will go into a database. And this is very advantageous when we distribute the file, because what we will end up doing is send to the user the exact bytes that we have on the archive. We will not decrypt them, re-encrypt them. We will not change a iota of those files, of those bytes, and we will just take the header and re-encrypt it so that only the user can get their hands into the yellow key. So the architecture is as follows. So the submitter will drop their files into an inbox that goes into a hard drive. The ingestion mechanism has access to the hard drive, of course, and you have different layers for the network between the external one, the internal one, and private one. There is a communication with central EGA through message queues, and the inbox knows the list of users through the authentication mechanism or the identity provider. This is the ingestion, and then the second part would be the distribution part. The distribution part would be that when the requester comes to this externally facing component, they request to download some file, and the dotted line is when the request is granted, then you go to the distribution mechanism that will fetch the files from the vault, re-encrypt the header, and send the new header for the user. So let me describe a little bit what happens in the distribution. The user is using a script that we provide to them. We fetch the credentials and the accession ID. We fetch the permission, and then we download the file. The technical aspect is in the last one, of course, and the other aspect are just help tools for the user so that it's convenient for them. And the technical aspect can be summarized with this following. So the green header was only used and readable by this local instance of the EGA. Even central EGA does not know how to read this header. So that means they cannot get their hands onto the yellow key, and that means they cannot decrypt the file itself. But when we send the file to the user, what we do is we make sure that there is absolutely no connection between the two entities, so that if you are a hacker and you get your hands on the blue encrypted data, there is, well, good luck decrypting it, because it's going to take like more than the age of the universe to decrypt it. And it's easier for you to go find the person of the original file and take their DNA, take samples and redo the DNA. You make sure that the headers are encrypted. And what we do is we send the new header to the user, the same data, and this data could be big, so it could be like gigabytes or terabytes of data sent to the user. All we re-encrypt is the header, and that leaves the question on the side, which is the transport. And you can transport the file over HTTPS, or you can transport the file over an SSH connection or an Aspera connection. So the transport is a little bit out of the equation. You can transport a little bit as you want, as long as the file is encrypted with Crypt4GH. It has advantages. So you have security through bearer tokens, through identity web-based tokens. You have SSH connections, centralized set of credentials. Oh, I have lots of questions. There is not much re-encryption going on the server, so there is not much load on the server. And then the implementation is microservice oriented, and there are some deployment using Kubernetes and Docker Swarm, but I will let Yusil describe them in the next presentation. So this was the architecture of an overview of the architecture. Lucille will describe more details for the architecture. This is the federated infrastructure. You package all that into a box. You connect multiple boxes, and we have 3 countries that have done that already. So NBIS in Sweden, CSC in Finland, and TSD in Norway, they have done that. And the question would be, who is the next one who wants to connect? And the reference implementation is on GitHub. So this is the organization, and this would be the repository. You have also some documentations, and this is local EGA in a nutshell in less than 15 minutes. Challenge accepted, and challenge I succeeded.